rerouting around failures, one about bootstrapping evolvability, and one about detecting BGP outages. Our first speaker is Thomas Holterbach, who's a second-year PhD student at ETH, and he did part of this work while interning at CADA. And he's going to tell us about rerouting around BGP failures. So, please.
Okay, thank you for the introduction. Hi, everyone. Today, I will show you how we can speed up the routing convergence in the internet. 2.5 minutes. 2.5 minutes is the worst case convergence time of an IP router upon an internet failure. And as a network operator, you clearly don't want that, because this could directly violate your SLAs and result in penalties. To start this presentation, let's take this very simple example. We have 3 routers, they speak BGP, and we focus on R1. R2 is the primary next hop, R3 is the backup next hop. So initially, the traffic goes from R1 to R2. Let's consider now we have a failure between R1 and R2. Upon the failure, R1 will have to converge. The BGP convergence typically has 2 phases. First, R1 needs to learn about the failure, then it needs to update its forwarding table. The learning phase essentially consists in this case, waiting that the BGP timer expires. And then R1 will have to update its forwarding table. And currently in the internet, there are more than 600,000 prefixes that are advertised. So R1 will have to update 600,000 entries in its forwarding table one by one. And this is a very slow process, which can take minutes. Fortunately, recently, many BGP fast reroute techniques have been designed. And some of them are actually used in practice. For instance, to speed up the learning phase, we can play with the BGP timers or use bidirectional forwarding detection protocol. To speed up the updating phase, we can use prefix-independent conversions or use MPLS fast reroute. The problem, though, is that none of those techniques can locally fast reroute upon remote outages. So if we take the previous example, and now we had a link between R2 and R4. And we say that this link fails. Well, R1 cannot fast reroute even if it does use fast reroute techniques, because R1 does not know the status of the link between R2 and R4. So it will have to wait that R2 sends to him withdrawals, and then it can converge. Remote outages are actually an important problem, because first, they are numerous. So we analyzed BGP sessions from root views and repris, and we looked for bursts of BGP withdrawals. We focused on withdrawals because they indicate unreachability, which happens whenever there is an outage. So usually, the number of withdrawals is quite low. But whenever an outage happens, we observe a peak of BGP withdrawals. So we use a 10-second sliding window here, and we compute the number of withdrawals on every window. And this enables us to know the start and the end of each burst. Using this methodology, we found more than 3,000 of bursts in November 2016, and considering 213 BGP sessions. Remote outages also propagate slowly. So we took all the bursts we observed in November 2016, and we plot in this graph their duration. So we can see that many of them take few seconds to completely arrive. And 37% of them actually take more than 10 seconds to arrive. And this is quite a long time, because during that time, the traffic is lost. So we actually confirmed this in our lab. So what we did is that we did exactly the previous network. We built it in our lab with real hardware, and then we simulated a remote failure, and we measured the convergence time with BGP. So in this case, we advertised a total of 280,000 prefixes, which is half of the current internet routing table. And then we observed a convergence time of 110 seconds. Again, we can see that we have packet lost during the entire time here. Today, I will present you Swift. Swift is a predictive fast reroute framework, and the cool thing with Swift is that it works upon remote outages. So first, I will show you that Swift reduces the learning time of a withdrawals by using from 13 seconds to 2 milliseconds by using a control plane prediction algorithm. Then I will show you that Swift can fast reroute the affected traffic toward unaffected path within only 40 milliseconds using a hierarchical forwarding table. And to finish with Swift, I will show you that it's deployable on existing routers. Let's first focus on the control plane prediction algorithm. Swift can predict the extent of an outage using a fast yet precise root cause analysis algorithm. So the existing root cause analysis solutions, they are able to precisely locate the failure. And to do that, they generally use several vantage points and sometimes active measurement as well. And by doing so, they often need minutes to locate the failure. Swift has different requirements. We designed Swift such that it trades some accuracy to gain speed. So Swift will return a region including the outage. And by doing so, we just need one vantage point, and we can also be very fast. Generally, we need a couple of seconds to locate the failure. To illustrate the algorithm, let's consider this simple network. We have few ISs, and we say that IS1 runs Swift. We say that IS5, 7, and 8 each advertise a different set of prefixes. And then we say that the link between 5 and 6 fails. Upon the failure, IS5 will then send BGP updates and withdrawals toward IS1. So Swift in IS1 will monitor the withdrawals. Prior to the failure, the number of withdrawals is quite low. Upon the failure, we will observe a peak of withdrawals. Then Swift will run a link inference algorithm. This link inference algorithm will compute for each link in the IS graph a link failure probability, and will return the link with the highest link failure probability, AD, for example, in this case. And then with this knowledge, Swift can then predict the entire burst of withdrawals very early in the burst. And this enables Swift to be very fast. The idea behind the prediction here is that Swift says that all the prefixes that are still using the failed link will be withdrawn very soon. Coming back to our previous example, Swift, the intuition here is that Swift actually take into account the prefixes that are going down, but also the prefixes that are still up. For instance, before the failure, all the links in the network can fail. So the candidate set is 2.5, 5.6, 6.7, and 6.8. I am not including 1.2 here because 1.2 is a local link. I am not including 3 as well because 3 is another BGP neighbor, and this algorithm is run on a per BGP neighbors basis. When Swift receives some withdrawals for the prefixes advertised by IS7, Swift can remove 6.8 from the candidate set because if 6.8 was the failed link, we should not observe withdrawal for the prefixes advertised by IS7. And then when Swift receives some withdrawals for the prefixes advertised by IS8, for the same reasons, Swift can remove 6.8 from the candidate set. Swift also leverages unaffected prefixes. The unaffected prefixes here are the 1,000 prefixes advertised by IS5. Swift can remove 2.5 because if 2.5 was the failed link, we should observe withdrawals for those prefixes here. In the end, Swift finds that 5.6 is the failed link, which is indeed true in this case. In practice, though, the withdrawals can arrive in a different order. Although we may have BGP noise is typically withdrawals that are unrelated to the failure. So we use two metrics in practice, which are computed on a per S-link basis. We use the withdrawal share as well as the path sharing. The withdrawal share is the fraction of the withdrawals that are crossing the link L. And the path sharing is the proportion of the prefixes withdrawn on the link L. Then we multiply those two metrics, and this gives us the fit score. The fit score is just a number between 0 and 1. 0 means that the link failure probability is very low. 1 means that it's very high. So typically, the links that are close to the failure have a high fit score. Otherwise, they have a low fit score. Using this algorithm, we then have the following theorem, which says that under perfect conditions, Swift always returns a set of links, including the failed one. There are some challenges, though. The first challenge is that we want to be fast. So we cannot wait the end of the burst before we trigger the fast reroute process. So to solve this challenge, we actually configure Swift to run the prediction very early during the burst, so as we can predict the burst. The second challenge is that an outage can affect multiple IS links. For instance, if you have one BGP router which has several BGP sessions, and that router here becomes down, multiple IS links in the graph can fail. So to solve this challenge, we configure Swift to return a set of links, all of them having a half-bit score, to be sure that we do not miss any failed link. Let's now focus on the accuracy of this link inference algorithm. So to measure the accuracy, we took all the bursts we have detected in 2016, and then we compute the true positive rate and the false positive rates. And here are the results. So in the bottom right corner, here are the cases that we really don't want to have. In those cases, we reroute many prefixes that are completely unrelated to the failure, and we do not reroute the prefixes that are actually affected by the failure. And the good thing here is that we can see we are never in this part of the figure. The corner on the top right are the cases where Swift actually reroutes the affected prefix, but also reroutes many unaffected prefixes. So here we have around 5% of the cases which are on this corner. On the bottom left corner, we have the cases where Swift actually misses to reroute some affected prefixes. So those prefixes will then converge with BGP. And then on the top left corner, we have all the cases where Swift works well, where we do have a fast convergence thanks to Swift. And here we have 85% of the cases in that corner, which indicates that overall, the accuracy is pretty good. Thanks to this link inference algorithm, Swift is much faster than BGP. So we computed that the median learning time of a withdrawal is 13 seconds with BGP. With Swift, it is just 2 seconds. So now I will show you that Swift can fast reroute the affected traffic toward unaffected backup path in 40 milliseconds only. There are a few challenges here, though. The first challenge is that any set of prefixes can be affected by a remote outage, and we don't know that set in advance. The second challenge is that the backup path can also be affected by the failure. So we want to be sure to use a backup path which is not affected by the failure. And finally, we want to be fast, of course. So to solve all these challenges, we will use a hierarchical forwarding table. In our hierarchical forwarding table, we have 2 tables. We have the mapping table and the pointer table. And then we use pointers to make the connection between the 2 tables. So for example, here, one data plane rule in the pointer table can actually reroute the traffic for all the prefixes that are sharing that pointers. And this makes the conversions very fast. Swift actually uses custom pointers, here in blue. And in those custom pointers, Swift first indicates the primary next stop to use for each prefix here. So now in the pointer table, Swift adds 2, prior to the failure, Swift adds 2 data plane rules. The first one matches on A, and then star everywhere else, and then forward the traffic to the out port number 1. And then there is another data plane rule, which matches on E, and then forward the traffic toward the out port number 2. Then Swift also encodes in the pointers the IS path each prefix is using. So for example, for that prefix here, F means that this prefix is traversing the link 5.6. B means this prefix is traversing the link 6.7, and so on. So now, upon the failure of the links between 5.6, Swift adds a high priority rule in the pointer table, which matches on F. And this single data plane rule will reroute all the traffic traversing the link 5.6. And this makes the conversions very fast. The problem, though, is that we still have to choose a backup next stop which is not affected by the failure. Right? So if we look at the previous example, and we now consider two backup next stop, 3 and 4. Well, maybe BGP, upon the failure, will use 4 because it has a higher local preference, for instance. We actually don't want Swift to use 4 because 4 uses the failed link here, so we would lose connectivity. So I will show you that Swift actually will use 3 instead. 3 is not affected by the failure in this case. So Swift actually does this by encoding in the pointers the backup next stop to use should any of the encoded link fail. For instance, C indicates the backup to use if the link between 5.6 fails. 3 indicates the backup next stop to use if the link 6.7 fails, and so on. So now, upon the failure of the link 5.6, Swift adds a high priority data plane rule in the pointer table, matching on F to reroute all the traffic traversing 5.6, and matching on 3 as well. 3 indicates a backup next stop which is not affected by the failure. Right? The pointers, though, have a limited number of bits. Right? They have 48 bits. I will explain why 48 later, but let's consider 48 bits for now. In the pointers, we then need to encode two different information, the AS path, as well as the primary and backup next stop to use. The problem, though, is that it's not possible to encode the entire AS graph in the pointers because there are too many AS links. So we have designed an encoding algorithm which only encodes in the pointers the most important AS links. And the most important AS links are the links having a high number of prefixes traversing them. Right? Because if one of them fails, it would imply downtime for many destination prefixes. So then we have measured the performance of this encoding algorithm. And to do that, we defined the encoding performance. The encoding performance is just the ratio between the number of prefixes that Swift can reroute with the number of prefixes that Swift would like to reroute. So with 13 bits, we can see that even if the median is good, we still have many cases where Swift cannot reroute the affected traffic because the links are not encoded in the pointers. With 18-bit, though, the results become much better. So the median case is 99%, and in most of the cases, Swift can reroute the affected traffic. So for now and for the rest of this presentation, I will consider that we use 18 bits. But it's still possible to use more bits here to get an even better accuracy. So we use 18 bits to encode the AS path, and this gives us 30 bits to encode the primary and backup next stop in the pointer. And 30 bits are enough to encode a large number of primary and backup next stop. So putting everything together now, we computed that Swift requires less than 100 forwarding updates to reroute the affected traffic towards an affected path. And here I am considering 16 backup next stop. And 100 forwarding entries is very fast. With current hardware, just 40 milliseconds are enough. So to finish with Swift, I would like to show that it's deployable on existing routers. It's deployable on existing routers because many of them already have a hierarchical forwarding table. So for those routers, a simple software update is required to deploy Swift. But what if we have a router which does not have a hierarchical forwarding table? Well, we actually found a way to deploy Swift on any existing routers. To do that, we take our hierarchical forwarding table, and we put the mapping table in the IP router, and the pointer table in an SDN switch, which is directly connected to the IP router. And then for the pointer, we use the destination MAC address. The destination MAC address has 48 bits, so this is where the 48-bit actually comes from. And then to program the destination MAC address, we use BGP and IRP. So we actually did this setup in our lab at ETH. We reproduce the network I just showed you before, and then we simulated a remote failure. We measured then the convergence time. So remember, again, with BGP, we observed a convergence time of 110 seconds. And with Swift, we observed a convergence time of just 2 seconds. So this is a 98% speed-up improvement thanks to Swift. To conclude this talk, I showed you that Swift can speed up the learning phase of the BGP convergence by predicting the control plane. Swift can quickly fast reroute the affected traffic to unaffected backup path. And Swift is deployable on existing routers with just a simple software update. For more information, please visit our website. We have the source code, a VM, and a demo as well. Thank you very much, and I will be happy to take your questions.
Ethan Katzbass at Columbia. Neat talk. I just had a small clarifying question. In the graph towards the beginning where you had the false positives and true positives, yes. I wasn't clear what the ground truth was. Is it just whether or not a particular prefix is going to be withdrawn, or are you claiming ground truth in terms of which link failed?
Yeah, so the problem is that when we take the data from read views and write prefix, is that we don't know which link has actually failed. Right. So we use indeed the actual prefixes that have been withdrawn to compute this false positive, this false positive rate and true positive rate. Right?
So it's predictions on which are going to be withdrawn at the time when you do it, and then if they're later withdrawn, it's a true positive?
Exactly, yes. Okay. However, we also did another experiment that I've not shown in that slide, is that we actually use CBGP, which is a BGP control plane simulator, and here we had the ground truth. So we simulated failure in this simulator, and then we also observed that Swift works well even at pinpointing the actual outage. Yeah.
Okay, thanks.
Yeah, sure.
And one more question. So what do you think are the main factors behind the 13-second number?
Sorry?
What are the main factors behind the 13 seconds number? Why is BGP so slow to work?
Well, first, I mean, remote outages, the thing is that they are remote. So the information needs to propagate through the network, and then each router in the path will have to process the BGP messages, go through the BGP decision process, and then send the result on the next router, and so on. So I think that could explain why it's slow to actually receive this information. Yeah. Mm-hmm.
Thank you. Thanks again.